Welcome to Advanced Reverse Engineering. There's homework due on the 31st of August. I don't think I need to go too in-depth into this. Take the text there on the screen and turn that into an executable program and run it. Let's talk about some other tools, and in particular, let's talk about strings. So strings is a neat little utility available on the most platforms, and what it does is it searches through a binary file looking for what appear to be null terminated strings, and it prints them out. So if we point it to, for example, this little program called hello, it finds hello world in there. It finds, oddly enough, hello.asm in there, which is the source file. It finds some done message len. Those are labels in the original program. It finds some other stuff. It finds these things with dots. It finds a whole bunch of interesting stuff in there. It's very useful when you're starting to reverse engineer a program to use something like this to help you get an overview of what may be left over in the program. Now, clearly, if you're doing something malicious, you don't want to help the reverse engineers out in the world do their work. I encourage you to help us do our work by leaving the strings in your file like this. But you can also use a command called strip to remove most of these. So, for example, if we pointed at certain other files, like let's point it at Python 3, it'll find lots of things that aren't necessarily strings, but sort of look like that, and print them out. You may recognize the shebang here, but for the most part, it's going to find gibberish. It's going to find real strings. It's a mixed bag. In that same vein, there's a tool called name. This lists the symbols that are present in an object file. And this is different from listing the strings. This actually goes and looks in symbol tables that are part of the object file, and we'll have a separate video on looking at the symbol tables, and prints those out. And you can see here we have a symbol called done, and it has a value associated with it. Symbols are going to have values associated with them. Sometimes very simple tools can reveal a lot about a program. Compilers will embed metadata in a program. Sometimes that can include even things like the name and email address of the person who wrote the code. You'd be surprised what you find when you look at the metadata that's present in a program. Let's go back to writing assembly and talk a little more about that. And in particular, let's look at a larger example of assembly. Last time we looked at a very, very, very simple one. Let's look at something that's a little more complicated. So let's write a program that computes the stopping time for a number sequence called the hailstone sequence. So in the hailstone sequence, we start with a number, and then we choose the next number in the sequence based on one of two rules. So let's pick a positive integer. That's what we start with. And let's pick 3. Now, here are two rules. If the number is even, divide it by 2. Well, 3 is odd, so that rule doesn't apply. The second rule is, if the number is odd, multiply it by 3 and add 1. Well, 3 is in fact odd, so we multiply it by 3 and get 9. We add 1 and get 10. And now we continue. We apply the rules again. If the number is even, divide it by 2. 10 is even, so we divide by 2 and get 5. 5 is odd, so we multiply by 3 to get 15 and add 1 to get 16. 16 is even, we divide by 2 and get 8. 8 is even, we divide by 2 and get 4. 4 is even, we divide by 2 and get 2. And 2 is even, we divide by 2 and get 1. Now, what happens at 1? 1 is odd, multiply it by 3 and add 1. That gives us 4, and then 2, 1. So 4, 2, 1, 4, 2, 1, 4, 2, 1 is this repeating sequence. So basically, we say once we reach 1, we stop. And the stopping time is the number of steps between our initial number, like 3, and 1. And so for the little sequence I gave you, the stopping time would be this step from 3 to 10, that's 1, 2 to 5, 3 to 16, 4 to 8, 5 to 4, 6 to 2, and 7, which takes us to 1. So the stopping time is 7. Okay? So for our little program, we're not going to bother with IO. We're just going to hard code the initial number. We'll do some other stuff later on, but for right now, let's just hard code the initial number. We're going to use the move instruction, so let's spend a little time thinking about it. MOV is pronounced move, and it copies bits from one place to another. So, for example, to copy the contents of RAX into RBX, we would say move RBX, comma, RAX. And again, this is the destination source order. RBX equals RAX, or RBX gets RAX, however you want to think about that. That's how it works. To move the immediate value, in this case hex 2120, into RAX, we'd write that. And so over here, this left argument is going to be a register or a memory reference. And the right argument could be an immediate value like 2120. It could be a register like RAX. It could be another memory reference. Now, memory to memory directly, we don't do. We'd have to put the memory into a register, then put that register into memory. But that's the basic gist of how this works. So it has several different addressing modes that I just covered: immediate, register, and indirect. And we'll see a lot. And the fun thing about move is it's Turing complete. And if you'd like to see that, there's a paper right here in this first really, which tells you about why move is Turing complete. And since it's Turing complete, it stands to reason I can rewrite any program as a program that only uses move. And there's a tool here at this link that does that. So fun stuff. We'll also need to use some kind of multiply instruction. We'll use mul, and there are two different versions of it, mul and imul. So mul multiplies unsigned values. Imul multiplies signed values. Okay? And I've got links to the details of the instructions over here if you want to go look at Felix's page on those. They don't quite work the same way. So what's going on here? Mul takes a single register or memory reference and multiplies RAX by that argument. Do you remember the div instruction from last time? How it had the implicit RDX and RAX registers? Mul does the same thing, except mul multiplies RAX by whatever argument you give it. Now that's a 64-bit argument being multiplied by some other 64-bit, potentially 64-bit thing. The result could be a 128-bit thing, and so the result goes in RDX, high bits go here, and RAX, low bits go here. And you'll need to notice that this changes what's in RDX. So if you are using the mul instruction, you need to be aware that it's going to overwrite RDX. Now, how does the imul instruction work? Well, it can work the same way as mul, with a single argument, just like that. Works exactly the same way, except it's using signed values. It treats RAX and RBX as if they have signed values. And we'll talk about 2's complement in a later class, but basically nothing tells you that a register is a signed or unsigned value. You have to know that and keep track of that yourself in your program. And then choose the appropriate instructions. It can take 2 arguments. So if I say imul RAX and 2, in this case, RDX is not used. It just takes the value in RAX, it multiplies it by 2, and it stores the result in RAX. And of course, that can overflow. 3 arguments, imul, RAX, RBX, and 2. What does that do? That takes RBX, it multiplies it by 2, and it stores the result in RAX. So there you go. This looks very much like an ARM instruction, but it's just the 3-argument version of the mul. And notice RDX is not involved in this. RDX is only involved when I have the single argument version, and I don't have the 2 and 3 argument versions for mul. So let's think what we do for odd numbers. For an odd number, we multiply it by 3 and we add 1. So that seems pretty reasonable. What I can do is I can put 3 in the register RBX. So now RBX holds the value 3. Now I can use the single argument version of mul. This has to be a register, and I can multiply that, and what I get is RAX times 3. And then I add 1 to RAX. So this presumes my current value is being stored in RAX. So if my current value is in RAX, these two instructions will multiply it by 3, and this one will add 1. And of course, RDX is going to be zeroed out by this, or it's going to get some other value. We won't worry about that for right now. What about for even numbers? Well, for even numbers, I'm going to use the div instruction we talked about last time. Now here, I'll need to be sure RDX is 0. So I'll go ahead and set it to 0. And we talked about why last time, right? If RDX has some value in it, and I divide, and there's a residue left over in RDX, that can cause a problem, because now it would overwrite part of the quotient with the remainder, and that will cause an exception. So I can't do that. So I don't want that to happen, so I'll put 0 in RDX. That means I'm dividing RAX by itself by 2. So I put 2 in RBX, and then I divide implicitly RAX by RBX explicitly. So this divides it by 2. So now I have code that multiplies by 3 and adds 1 for the odd case, and code that divides by 2 for the even case. Great. That seems like that was probably the hard stuff. What else do I need? Well, I need to know if a number is even or odd. How could we do that? Well, we don't know how to do much in assembly yet, but we do know how to divide by 2. And if you remember, division puts the remainder in RDX. So we can divide by 2 and look at the remainder. So we can do that by putting 2 in RBX, 0 in RDX, dividing RAX by RBX, and then we'll know, because RDX will tell us the remainder. The problem is this will also divide RAX by 2, which will change its value, but we want it to hold the current value. So let's save it. So we'll go ahead and put 2 in RBX, 0 in RDX, then we'll save RAX in a temporary register RCX. We'll save it temporarily in RCX. We'll do the division, and then we'll restore RAX from RCX. So you see what happens here is we store 2, put 0 in RDX so that we don't cause an exception, save RAX, divide RAX by 2, and then restore it. Now, where is our remainder going to be? It's going to be in RDX. So at this point, we need to then do something to see if RDX is 0. Because we're divided by 2, it's either going to be 0, meaning it was even, or it's going to be 1, meaning it was odd. Okay. An important point to note here is that the flags aren't modified by move. We're not going to use the flags right now, but it's worth just noting that point right here. So what we need to do next is compare RDX to 0 and see if it's equal to 0 or not. And the way to do that is to use the compare instruction. So here's the compare instruction. It's just CMP, and it compares its two arguments. The way that it does that is it does it by subtraction. But if you just clear your brain of that piece of information and just think about it as compare RDX to 0 and then jump if they are equal. Okay, that makes sense. Is RDX equal to 0? Then we'll jump down to the case even. So I'll put a label down here for even, and that's where we'll go. The even case will be put here. And what if it's not? What if this is not true? Well, then we'll fall into this next case, which will be the odd case. We'll put it here. So there we go. So we needed a new label. In this case, we used even with a colon to indicate this is a label. And we conditionally branch here if RDX is 0. So now we plugged in our two cases. Here's our odd case, multiply by 3 and add 1. Here's our even case, divide by 2. Great. So now we have the odd and the even case. Now, will this work? Is this what we want? Let's think. I flow through here. I come here and either I do this for the odd case or I come down here for the even case. But in the odd case, I just fall right through and do the even case. I don't want to do that. So I need something to help me get around the even case. I need a branch or a jump or something to take me around the even case. And I'll need another label. Let's call that label over. And we'll just pop it in like this. So now I do the odd case, I jump to over, or I do the even case and then I fall into over. So this has the traditional diamond shape of an if then else, right? I have the if up here, the then case, the else case, and then I come back together down here at the bottom. So there we go. This handles the whole process of figuring out if it's even or odd and then doing one of those two operations. Now I need to put it in a loop. And I need to keep track of the number of times the loop runs because that's what I really want. I want to know how long it takes to get to 1. So let's think about a while loop. What would a while loop look like in this world? Well, I'm going to initialize RSI to 0. This is going to hold the stopping time. I chose RSI for S for stopping just as a mnemonic device for myself. This will hold the stopping time, number of steps. And so here's the top of my loop. And at the top of my loop, I'm going to have the condition. It's a while loop, so I'm going to say, is RAX, is my current value equal to 1? And if it is, I will jump to done. Boom, go down here, and I'm done. Does that make sense? Let's say we come in and RX is initially 1. Well, then I'll set this to 0. I'll come in and I'll check it against 1. It's 1, so I'm done, which means that RSI remains 0, which is the correct answer for an initial value of 1. There are no steps taken to reach 1. So the initial case is still good. What if it's not 1? Well, then I add 1 to RSI. So I've added a step. Now I do that if then else code, right? I check to see if RX is even or odd. I do the appropriate thing, and then I jump unconditionally back to the top where I check the condition again. So each time I do something, I increment RSI by 1, jump back to the top. So here's my while do structure, and this should look pretty much like a normal while do structure to you. Great. So I just need to plug in the if then else code. I also do need to initialize, and I need to have something that ends the program. So before we talked about how to end the program, I'm going to do the same thing I did before here. 60 will go in RAX. That signals that it's an exit when I do a syscall. But then I'm going to have the exit value of the program be the stopping distance. So RSI holds RSI holds my stopping distance. And by convention, RDI holds the return value for the program when I do this last syscall. So I'll take the stopping distance that I've computed, I'll put it in RDI, and then I'm done. So RDI gets RSI, and then I exit. This is the return value, and I exit. At the start, I'll initialize RAX to the number I want to compute the stopping criteria for. I will use 27 here for that, and then I'll just plug the while loop in here. Putting it all together gives us this program, and you can see all the main pieces here. Now notice up at the top, I've gone ahead and said section.txt. We'll talk about sections later, but this basically says I'm going to start giving you the program. This is a executable program. Those go in your text section, and that's where we're going to start. We can rename this or do other things with it, but for right now, we'll just stay with the tried and true default. Our program goes in .text. We also declare start global so the linker can find it without complaining. And here we go. We initialize our value. We initialize our stopping distance number. Here's the top of our loop. We loop. We do a check. We have an odd case and an even case. We jump back to the top and check again. When we're done, we go to done. Done is down here. We put our stopping distance in RDI. We then exit, and that's it. So we can assemble this with NASM-elf F64. It tells us what kind of file we want. and then distance.asm, which is where we should put this. That will produce a distance.o file, which we can link. And so we do ld-o distance, that'll be our final executable, distance.o. In this case, it's just one file to link. Then we can run it. We run .distance, and we do a semicolon echo $? So we can see the return value, which turns out to be 111. Is that right? Well, there's an online tool available here that will let you compute the stopping time for any number you want to enter. Our initial value was 27, our result was 111, and that is in fact the correct stopping criteria for this. And this does it for anything, any positive integer, plug it in, and you'll get the correct stopping time. Great. So that's our initial version of our little program. But can we make it better? Well, let's think about some of the things that we can do in assembly. I mentioned before that bit shifting is really common. It's the way a lot of things are done in assembly. So we're using div to divide a number by 2. We can also use an instruction called shift right to do the same thing. Shift right just shifts the bits in a register or memory location right. So think about that. Over here we have some bits. The most significant bit is on the left. The least significant bit is on the right. And that's by convention how we write the number. And that's the same order we write the digits in a decimal number here. We write them with the most significant on the left and the least significant on the right. And so when we say shift right, we mean shift the bits toward the least significant end. Now, what happens at the top, right? Well, we need to fill this in. We fill it in with a 0. This instruction puts a 0 in here, and it takes the least significant bit and it puts it in the carry flag. So the carry flag is one of those flags in the flags register we talked about last time. This just overwrites carry with the bit that gets pushed out, because one bit has to be pushed out with this. So if I start with 837, I shift it right once, I wind up with 418 and a 1 in the carry flag. What happened? I divided 837 by 2 to get 418 with a remainder of 1. Pretty clever, huh? So, right, because it's just like if I shift a decimal number, if I shift the digits right by 1, it's like dividing the number by 10. If I shift it left by 1, it's like multiplying the number by 10. Well, this is base 2, same thing, but with the power of 2. So shifting RAX right by 1 is the same as dividing it by 2. And it's way simpler than using the div instruction. So we could do that. In fact, we could also use this to test even or odd by shifting once and looking at the carry flag. That would work. But there is, in fact, a better way to do a test for even or odd, and that is to use bit testing. Okay? A bit test takes 2 arguments, so here's one and here's another, and it performs a bitwise AND. And you remember how that works, right? 0 and 0 is 0. 0 and 1 is 0. 1 and 0 is 0. And 1 and 1 is 1. Right? So you only get a 1 when they are the same, when they are both 1s. So in this case, they're both 0, so we get a 0. That's true all along here. This is a 1 and a 0, so we get a 0. Finally, we wind up with 2 1s, and so we get a 1 down here. You can think of this as a bit mask. Sometimes people think of it as a bit mask. I set bits in here, and I only get bits where there are 1s in both. So it masks out some bits. In this case, I mask out the lowest order bit. Right? This is the bit that would have been shifted into the carry when I divided by 2. And this is, in fact, the bit that would be the remainder when dividing by 2. Right? Just like the lowest order digit in a decimal integer would be the remainder when dividing by 10. Right? 19 divided by 10 is 1 with a remainder of 9. In this case, this number, 837 divided by 2, would give me a remainder of 1, and I can check that. Now, where do I put the result? I got to store the result somewhere, right? No. The test instruction performs the bitwise AND but does not store the result. Wait, how is that useful? If it doesn't store the result, how can I know if there's a 1 here? That's because the test instruction sets flags, and in particular, it sets the 0 flag. If the result of this test is all zeros, the 0 flag will be set to 1. If it's got a 1 somewhere in it, or many ones, if it's not all zeros, this will be 0. So when I do this, and I get a 1, the 0 flag is clear. So I can check even by just doing a test, in this case of RAX and 1, and then checking to see if the result is 0. If the result is 0, right, then the initial thing must have been even. There must have been a 0 in this position. If it's not 0, the initial one must have been odd. And so I can just do a test. I don't have to worry about overriding a register because this doesn't store the result. All it does is set the 0 flag and some other flags. And that's all I've got to check. Well, that's great. So let's make those changes. So over here on the left-hand side, we have our original check to see if the number is even. We replace that with test RAX and 1 and jump on 0 to even. That's it. We don't have to worry about any other registers. That takes care of everything for us. In addition, down here in the even case, we've divided by 2. We can replace that with this, shift RAX right by 1. So that makes our code shorter. Shorter code is better for a number of reasons. It's fewer instructions being executed inside of a loop, right? And fewer instructions inside the loop means the loop is going to run faster, and the whole thing's going to run faster. Nicely done. There's more we can do. We added 1 to R. Remember, we had the RSI that held our stopping value, and each time we did an add of RSI and 1, we added 1 to it. We can also use the increment instruction, inc RSI, which would just increment RSI by 1 each time through. It's a simpler instruction. It's shorter. It's going to run probably about the same, honestly, about the same time as the add instruction, but it's what we would commonly use. We can replace multiply by 3 and add 1. There is, in fact, an instruction that will let us do that, and that instruction is load effective address. Okay? Just trust me on this. We'll see how to do that in a bit. And there are some other optimizations and common idioms that we could use. The point of this is that in order to be able to read assembly, you need to recognize these idioms when they occur and not just take the instructions at face value. Oh, this says shift by a certain number of positions. What's actually happening is I'm dividing or doing something else. I need to recognize those patterns. So here we go. A basic approach is to build your program in pieces and get each part working. Once it's working, you can optimize it later, but just get it working. And another thing to keep in mind is that the right way to do something in assembly is not always the same as the right way in a high-level language. No one's going to expect you to use the shift operators to divide a number in C. They're going to expect you to just divide because that's the obvious way to do it. They'll expect the compiler to make the correct adjustments. But in assembly, you've got to play the version of the compiler as well, and so you'll want to use the shift instructions. Let's talk about some instruction set architecture topics. The part number is wrong. Sorry about that. And the first one is Endianness, or byte order. So we have 2 primary byte orders. We can put the little end of a number first or the big end of a number first. Now, why does that come up? Well, suppose I have a value like 678. So I can store a value from 0 to 255 in a single byte. 678 is too large to be stored there. I need those low 8 bits, but then I need 2 more. So I really need a third byte to hold that information. I need a second byte to hold that information. Sorry, this would be the low byte, and this would go in the high byte. So I need 2 bytes. And then the question becomes, I don't care when it's in a register, but I care if I have to write it to memory and then read it back from memory. Then I need to know which byte do I put first. And obviously there are a couple different ways to do it, right? The high byte holds these 8 bits. The low byte holds those 8 bits. And I got to figure this out. I do point out here that this has not always been universal. There's different ways to encode the number. Some machines used packed BCD, which looked like this. A nibble was enough to hold a 0 through 9, and so sometimes we used 1 nibble for each. But that's gone, right? We tend to use this. I shouldn't say gone. It lives on in some 7-segment displays and a few other places. But for the most part, you don't need to worry about it. Right? This is how we've sort of agreed on encoding numbers. So we can store the high byte first or the low byte first. And by first, I mean at the lowest memory address. So say we're writing it to location 7. I could put the high byte at 7 and the low byte at 8, or I could put the low byte at 8 and the low byte at 7 and the high byte at 8. Anyway, I could put one of them first. And so we want to put them in consecutive addresses in A and A plus 1, but which byte goes where? Little Endian says put the low order byte at the low address. Big Endian says put the high order byte at the low address. And both exist and are very widely used. I would say that Little Endian tends to be winning out. I mentioned the 6800 processor before. It was a Big Endian processor. The x86 is a Little Endian processor. And ARM is configurable, but most of the time you'll find it being used in a Little Endian configuration, at least in most of the environments where you're likely to encounter it. Worth mentioning is network byte order. Suppose I have to send a multi-byte number over a network. Well, then I tend to use network byte order, which is big end, in that I send the big end of the number first, and then I send the little end after it. And this scales up to any number of bytes. If I've got an 8-byte number, right, I have 8 different bytes. Big Endian means send the most significant 8 bits, and then go all the way down until I get to the least significant 8 bits. Okay. So Little Endian, suppose I want to break this value, right, 2,255,081,000 in memory, and I want to divide that up into bytes and store it. In hexadecimal, we can write that value just like this. So highest nibble is here at 9, the lowest order is here at 8. And the highest order byte is 98, the lowest order byte is 28. So how am I going to put this down? Well, here's my highest order byte, next, and lowest order byte. If I store this as an 8-byte value in Little Endian, then I would store the 28, and then the 71, and then the 4B, and then the 98, and then 0000. All right. If I store it in Big Endian, then I would store it looking like this. The big end is over here. The little end is over here. And of course, in ratios, we don't care about this, but in memory, we do. You're going to have to think about this a little bit, because you'll see numbers in Little Endian when you look at disassembly. So here's a little piece of code at the top. I take this thing, I turn it into an 8-byte value, and I store it in RAX. My disassembly shows me that, yeah, that's the number I think it is, right here. But then when I look over here, I see something different. I see 2871 4B 98. Well, 2871 4B 98 is that number in Little Endian. I'll see it also when I look at the contents of certain parts of memory. Here's an obj dump. In this case, I'm looking at part of a header for a file. And I will see some stuff happening here, right? I'll see a file offset of 180. I'll see a size of 10. If I go and look at that location, again, there are the same bytes, but now they're in Little Endian order. Okay. As an aside, this is a good place to mention this. When I did this, and I assembled it, and I disassembled it, I got an instruction called move ABS. And you may wonder what that is. And you can look in the Intel manual for move ABS, and you won't find it. This is just move. This is some weird notation leaking in to the disassembly. So if I look at this if I look at a program in Ghidra, in the NSA Ghidra tool, I might see a disassembly that looks like this. If I look at it in the online disassembler, I might see a disassembly that looks like this. Exactly the same thing, right? Push RBP and move, push and move. Then I have this move, but over here I have a move ABS, right? Weird, right? If I try to put a move ABS in my assembler, it will complain. This is just a weird notational thing. Let's talk about 2's complement numbers. So how do I represent a negative number? Well, one way would be to complement it by flipping all the bits. We call that the 1's complement. So I have 87. I want to represent negative 87. So I flip all the bits, right? I flip this one to a 1, this next one to a 0, then a 1, then a 0, 1, 0, 0, 0. And I could represent that as subtracting it from the highest value I could store. So 255 is all the bits set. I subtract 87 from that, and I wind up with this value down here. That's the 1's complement. The value can run from negative 2 to the n minus 1, because I have to use that top bit to indicate negative, or positive. If it's a 1, it's negative. If it's a 0, it's positive. All the way up to 2 to the n. Very convenient. Minus 2 to the n minus 1 up to 2 to the n minus 1. Every positive and negative number has the expected complement, but there's also a weirdness that there is a 0 and a negative 0, right? This represents negative 0, which is weird, and all zeros represents 0. You'll see this if you have like an old TI calculator. You can sometimes get negative 0, and it does some weird stuff. Math doesn't necessarily work the way we want it to with 1's complement. If I'm at 0 and I subtract 1, I wind up with that, which is negative 0. That doesn't seem right. So now I have to keep track of when I cross 0. And that's true even when I have something like 3 plus a negative 2. I wind up with the wrong result in this case if I'm not careful. I have to be sure and do an initial increment or decrement to be sure I get the right answer. So with that out of the way, we can forget about 1's complement because history has forgotten about it in favor of 2's complement. Another way is to get the negative of a number is to basically subtract it from 0. That's what we would normally do, right? And so I want to subtract 87 from 0, and so I represent 0 here with a 1 over here, so I have something to borrow from, and all zeros. And when I do that, and I subtract, I wind up with this, which you notice the bits didn't just flip, something else happened, right? I may have flipped all the bits and then I added 1, that's another way to think of it. And that gave me negative 87, or gives me what I'll think of now as negative 87. And there are a number of ways to think about this, right? This bit is 1, 2, 4, 8, 16, 32, 64, 128. A way to think about this, a way to read this binary representation, is to take the top bit and make it negative. So this means negative 128. All the other bits are positive. Negative 128 bits plus 32 plus 8 plus 1. So that's negative 128 plus 41, which gives me 87. And I just have to remember that it's negative. That's another way to think about this, negative 87. So the value can now run from negative 2 to the n minus 1 up to 2 to the n minus 1. Well, that's odd. It's not very symmetric. And that's because we have a single 0 now, which is all the zeros, which, and since it's an even number of numbers we can represent, one of those is being used for 0. The two sides have to be lopsided. And this is important to understand. This means it doesn't matter whether we consider numbers to be signed or unsigned. for most things. For addition, it doesn't matter, right? The right thing will happen when I add or subtract two numbers in 2's complement. It will just do the right thing. And so I don't have to keep track of whether they're signed or unsigned. And that's great. Okay, so if I take 3 and I add -2, I represent 3, represent -2 over here by subtracting from all zeros with the 1 there for carry, or for borrow. I get this. When I add those, I get 1, which is the correct answer. It works. It just works the way you want it to work. And so that's why we all use and love 2's complement. Okay. Another way, as I said before, is to think of flipping all the bits and then adding 1. So if I start with 2, I flip all the bits, then I add 1, and I get that. Fine. That will work too. Whatever helps you remember this. It's still a trade-off. There's a weirdness. If I take a -128 and it's represented like this, and I negate it, so I do a negative of 128, I would represent I'd flip all the bits and add 1, and I wind up with this, which means negating -128 gives me -128. I can't represent the value 128 in 8-bit 2's complement, which means this number doesn't have a positive version. Just something you have to live with. Okay, nothing about a register marks it as signed or unsigned. It's just bits, and it's up to you, the programmer, to keep track of that. And it matters for some operations. So it doesn't matter for add and sub, but it does matter for multiply and divide, and IMUL and IDIV. Now, what about shifts? Right? I used shift before to divide by 2, and that shifted all the bits over. In particular, it would shift the sign bit over. And that would mean if I divide a negative number by 2, I wind up with a positive number. And that's not right. Well, it turns out there are instructions specifically for that, and they are shift arithmetic left and shift arithmetic right. They preserve the sign bit and shift all the other bits so that you get the correct answer. So if I take -16 and I divide by 2, I get -8, as I would expect to get. The sign bit matters for certain other kinds of operations. It doesn't matter for compare. Compare does its compare by subtracting, and we already agreed that it doesn't matter for subtracting, but it does matter for the result, right? What if it's an unsigned compare and I subtract and the high bit is set? Well, it's a big positive number. What if it's a signed numbers that I subtract and the high bit is set? Well, then it's a big negative number. I got to keep track of that. And so it doesn't matter for this, but it matters for what I do after. So there's a jump if equal and a jump if not equal, right? Those don't have to change. Same thing for jump 0 and jump not 0, which are synonyms for those. Jump greater and jump greater than or equal, jump less than or equal, and jump less than all interpret the result of compare as if the operands are signed. And then jump above equal, below equal, and below interpret as if the operations were unsigned. We'll go over this again in the future. Okay? So let's talk about conditional branches. So I mentioned compare does its work by subtracting. And when it subtracts, it sets all the flags appropriately. We'll ignore the auxiliary flag, which is the first one and is in gray. Don't worry about it. Just you can pretend it's not there for the most part. The carry flag is set if the entire subtraction required a borrow. So think about comparing hex 21 and hex 31. So I'm going to do that comparison by subtracting the second one from the first one. So compare of 21, 31 would subtract 31 from 21. Well, clearly the second one is larger, so the result is going to be negative, which will require a borrow. And so the carry flag will be set. Make sense? If I subtract hex 17 from hex 21, I can do that without requiring a borrow, so the carry flag is clear. right? So the carry flag is going to be set when the second argument is larger than the first argument. How about the overflow flag? This is set if the most significant bit, that is the sign bit, of the result is different from the most significant bit of the first operand. What? Well, that will happen when the sign changes. So suppose I compare -2, -3. So compare -2, -3. First argument is -2, second is -3. I do that by subtracting. So that's -2 minus -3, which is the same as -2 plus 3, which is 1. That's positive. The original first argument was negative, so the sign bit flipped, and the overflow flag is set. The parity flag is set if the number of ones in the least significant byte of the result is even. Why do I care about that? Who knows, right? You can think of it as the number of ones being even, or you can think of it as the number of zeros being even, right? They happen the same way. The sign flag is set if the result of the subtraction is negative in the two's complement sense. So let's say I again compare 21 and 24 in that order. I'm subtracting 24 from 21. The result is going to be a negative value, so the sign flag will be set. And the zero flag is set if the two operands are equal, and so their subtraction results in 0. So if I did a compare of 21 with 21, I would get 0. So that's how these flags get set. Now, based on that, based on just those 5 flags, I have a lot of options. And here they are. So I mentioned jump if above. When does that happen? That happens when the carry flag is clear and the zero flag is clear. Above or equal, that happens when the carry flag is clear, right? The difference is that the zero flag is not checked here. And so on. If you want to figure all these out, you're welcome to. But, you know, they are what they are. This is one way to think about all the different types of conditional instructions. And here they are in all their glory. I think they're alphabetical. That's not the best way to think about them. I tend to prefer looking at them this way. So here I have above and below, and I use these for unsigned numbers. And so I have jump above, jump not below or equal. So wait, you might say, jump above, jump not below or equal. Those sound like the same thing, and they are. Things that are in columns here are synonyms. Things that are in rows are antonyms. So the opposite of jump above is jump not above. The opposite of jump not below or equal is jump below or equal. Okay? Well, what about jump below? It's down here. Here's jump below, jump not below, jump not above or equal, which is a synonym, jump above or equal. And then look at this. Jump if the carry is set and jump if the carry is not set. It turns out those are all synonyms. Okay? Because what jump below tests is just the carry flag. And so that's a synonym for checking the carry flag. So synonyms here, antonyms here. And here's a little reminder here in case you forget. Greater than or less than are used for sign numbers. And so we have the usual ones here and down here. Nothing is so simple, as you can tell by the tops of the columns, that it doesn't just convert to carry checking over here. They're a little more complicated. Equality, jump if equal, is the same as jump zero. They just check the zero flag, right? Because we're subtracting. And when things are equal and we subtract them, we get 0. Same for not equal and not 0. Now, an interesting thing to note is that in my assembly, I might write jump if equal. And that will be converted to some machine instructions. And it'll be converted to exactly the same machine instructions as if I'd written jump 0. Then later on, when I disassemble, I might see jump 0 instead and go, oh, well, that's odd. I said jump equal. Well, those synonyms. That can show up and be a little confusing if I write something like jump greater than, and the disassembler shows me jump not less than or equal, or the opposite, right? Those look very different, but they're really the same thing. I can explicitly check the flags. Over here, I checked carry, right? I have jump if carry and jump not carry. Over here, I can check the overflow flag by itself, jump if overflow and jump if not overflow, the sign flag, and the parity flag. And I have some synonyms for that, right? Jump if the parity flag is set, jump if the parity flag is clear. Parity flag being set is a synonym, which is jump if parity even, and then over here is jump if parity odd. Now, those all make sense. They all use the flags, and life is good. I have simple synonyms, antonyms, life is great. But then I have this additional thing here at the bottom middle, which is the count register. Remember I said RCX had some special stuff associated with it. I can check the content of the count register and jump if the entire register is 0. If RCX equals 0, I can check that with jump RCX 0. If I just check the bottom 32 bits, that's jump ECX 0. And if I just check the bottom 16 bits, that's jump CX 0. And you'll sometimes see this, although it's not that common as it used to be. All right. ObjJump likes some of these more than others. And the ones that you will see in ObjJump have a little asterisk by them. So if I write jump not above, I will see jump below or equal when I look at it in ObjJump. Let's talk about memory references. We've already seen a couple of them, but let's now pull that apart and look at the syntax for memory references. Remember how they work in C. Okay? Memory references in C have a base. In this case, we're using, let's say we have an array called R, and the base array, the thing by itself, is just a pointer to a location in memory, pointer to this byte right here. And every entry, let's say, is an int, and each int is 4 bytes. So here I have the first entry, which is 4 bytes. The second entry is 4 more, the third, and so on. And the way indexing works is 0 based. So this array 0 is these 4 bytes. Array 1 is these 4, 2, 3, and here's array 4. It's the 5th entry, and it occurs right here. All right, so we understand, I hope, how that works. You have a base, which is the array itself, R. That's our base. We have an index. In this case, it's 4. And the way we move forward is by multiplying the index by the scale. And so the scale is 4, right? The size of each thing is 4. So 4 times 4 gives us 16. Right? Here we are at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? So that gives us the correct offset. It's base plus index times scale. We might want a particular byte out of that. And if we did that, we'd take the base, we'd add the index times the scale, and then we'd add the offset. So if we added an offset of 1, we'd go here to this byte right here. And we could represent it like this. Because C tries to do pointer arithmetic, we'll cast array to a byte pointer. We'll add 7 times the size of int, and then we'll add 1. And this expression will give us this location right here. And this shows us some important pieces. Here's our base. Here's our index. Here's our scale. And here's an offset. And that's exactly how memory addressing works in the Intel dialect of x86 assembly. Now, it's present in the AT&T dialect. It just has a different syntax. Okay. So what we'll see is square brackets around it, and in all but one case, the square brackets mean indirection. They're like the star in C. They're going to compute what's inside here and then go get the contents of memory there and replace this whole thing with the contents. And what we have is a base, an index, times a scale, plus a displacement. All right? think what things would be variables and what things would be constants in your program, right? Your base would be the array pointer. That would be a variable, the name of the array. The scale would be some number, some fixed number, right? It would be like 4 for an int or 1 for a byte. But the index would probably be a variable, right? It would be something like x. And the displacement would be some constant value. And if you think about it like that, this is going to make some sense. The base is given by a general purpose register. What are those? Those are the 16 registers you see at the bottom here. You can use any of those as the base. And yes, the stack pointer and the base pointer are included in that. So there they are. Any of those could be the base. The index is given by a general purpose register. Okay? What if I don't give you a base? Well, it's 0. What if I don't give you an index? Well, it's 0. The scale has to be 1, 2, 4, or 8. If I don't give you a scale, the scale is 1. Right? And the displacement is an integer literal, and by default, it's 0. Okay? I think this sounds complicated, but it's going to make a lot of sense as we go through some examples. In case you're curious as to where all this takes place in your assembly code, because you might look for some of this in your assembly and wonder where the heck it is, a lot of this information is encoded in a SIB byte, which is a special kind of prefix byte. SIB stands for scale index base. Right? Displacement has to be a literal in the bytes itself. And that's one of the prefix bytes you can have. There's other ones. The mod RM byte is one. And you can read about these online if you want. So let's look at some examples. So here we have 1028 in brackets. That is displacement only. And it can be interpreted as just the address 1028. Right? What's my base? 0. What's my index? 0. My scale is 1. 0 times 1 is 0. I add all those together, plus my displacement 1028, and I get 1028. Boom, done. How about this? Base only. Right? I take RAX. That tells me go look at the location pointed to by RAX. Could I think of RAX as being my index? Sure, I could. Index times the default scale of 1 is just the index, plus a base of 0 and a displacement of 0. There you go, right? It doesn't matter how you want to think about it. That's perfectly fine. Base plus displacement. So this takes my base in RAX, adds 1028 to it, and I go to that address. Base and index. Really? Yes. Right? Base, either one of those could be the base. Either one of those could be the index, because since the scale is not given, it's 1. And RDX times 1 plus RAX is the same as RDX plus RAX times 1, right? Don't know, don't care. That works just fine. What about this? That's index and scale only, and that's perfectly fine. Here the scale is 2. Here we have index, scale, and displacement. So I have a base of 0. I have an index in RAX, a scale of 4. So that's like going through our int list. And then I have a displacement of 2. Here I have all the pieces. I have a base of RDX. I have RAX, which is my index. I multiply it by 8. And then I add 2. Okay. This is the Intel syntax. AT&T syntax is different. And the order of the parts in all of the things you see here doesn't matter. The assembler will figure it out. That's one of the nice things about the Intel dialect, is that the assembler will just sort of figure it all out and try to do the right thing. And how it encodes it, entirely up to it. Does it want to encode RAX here as the index or as the base? Doesn't matter. Doesn't matter. Either one's fine. It'll figure it out. The address arithmetic we just did is super useful. For example, we can use it to figure out 3n plus 1. But wait, how do we do that? How can we figure out 3n plus 1 using this approach? Well, remember that RAX contained our stopping distance, or RAX contained our current number, excuse me. We wanted to multiply our number by 3 and add 1. Well, look at this. I treat RAX as the base. I treat it as the index also and multiply it by 2. RAX times 2 plus RAX is in fact 3 times RAX, and then I add 1. So this value right here it gives us RAX times 3 plus 1, and it would do it in a single instruction because there's special hardware in the processor to compute these addresses. But it's a memory reference, right? I mean, we don't want to get the content of memory at this address. I just want to know what that address is. There's a special instruction for that, and it's load effective address. Load effective address takes whatever's over here as an address calculation and puts this value, not the contents of this, but the value itself, in RAX. So this instruction will compute RAX gets 3 times RAX plus 1. That's what it will do. Now, an important thing to note. The registers that appear inside these square brackets have to be 64-bit registers because addresses are 64 bits. So I got to use the R version of them. And I've got to be careful about everything in here being a 64-byte thing. And we'll see that come up later on. This is the only time I'm aware of that the square brackets around the thing don't really mean indirection. Okay, every other time they're going to mean indirection. Go and get something out of memory. Here they don't. And so you'll need to watch this. If this were move, I'd go and get the contents of this address and put it in RAX. But because it's LEA, I get this address and put the address in RAX. So let's use this optimization in our program. Let's go back to our little program we had before. Let's substitute the odd case for the odd case. There it is. Look at that. Simplified it so much. The odd case is that. The even case is just a shift right. I've still got the test up here for this. You know, our program is looking less and less like it did initially, less and less obvious, but it's containing more and more common assembly idioms. Okay, now, sometimes when I reference something in memory, or I want to put something in memory, the assembler is not going to know what I mean, and I've got to give it a hint. So let's say I just said move into the location pointed to by RAX the value 17. If I just did that, the assembler would complain. It would say, I don't know how wide you want that 17 to be. Do you mean it to be a byte or a double word or a quad word? What do you mean? And so here I've explicitly said I want this 17 to be a double word. So I've cast 17 to be a double word, which means that now it's a 4-byte 17, right? So it's 17 in the low order byte and then 3 zeros. And that's what will get put in memory starting at the location pointed to by RAX. I can also cast the receiver here, RAX's location, this memory address, to be a double word, and then I put 17 in it. Either one of these will work. It tells the assembler what I mean. I want to put a 32-bit or a 4-byte version of 17 into the memory address pointed to by RAX. So here's some examples. Here I take the byte that's at address 60 and I put it in AL. Do I need to say byte? Well, AL is a byte size register, so no, I don't. This would work without me saying byte. But it will probably segfault because I probably don't have anything at address 60. It's not mapped into my virtual address space, and so something bad will happen. If I were in an embedded environment, this might work just fine. Down here, I take the word that's at the address pointed to by RAX, and I put it in AX, 16-bit register, so it's going to expect to get 16 bits from here. So I may not need word here, but I can include it if I want to be explicit. Down here, go to the location pointed to by RAX plus 60 and store the 32 bits that are in EBX at this location. put the 8-byte contents of RSI into this location. And then finally, compute this address and put the address in RSI. And I give you the computations over here. Let's talk about register aliases again. Remember, RAX is the big register, right? It's 64 bits. So it's 1, 2, 3, 4, 5, 6, 7, 8 bytes long. RAX refers to these bits. EAX refers to the low 32 bits. AX refers to the low 16, and AH and AL refer to one of the two low bytes. And that's how that works. So those are aliases, and that's true for all the different register aliases that we have. Now, what do we have? Well, we have these. So we have these R registers, which are 64 bits. They have 32-bit aliases, 16-bit aliases, and 8-bit aliases. Well, Stacy, you say, why don't we have 8-bit aliases for these guys? And for that matter, why isn't there a 32-bit, a 16-bit, or an 8-bit alias for this, right? I want to see, instead of R8, I want an E8, right? And then maybe, I don't know what this would be, 8? And 8H, AL, 8L. I want to see those. Well, you're in luck. We went ahead with the people who maintained the chip went ahead and added access to the low byte of these registers. And instead of saying, SL, they said SIL. And that kind of makes sense because there's not an X there to replace. So SIL is the low byte of the RSI register. DIL is the low byte of RDI. BPL for RBP, and SPL for RSP. Great! So we'll just follow that same pattern over here, and we could do the other ones as well, except of course we don't. What we do instead for these is they are R8D for the double word, the low 32 bits of that, W for the low 16, and B for the low 8. And there you go. Well, why didn't they use this for this? They could have said, RSIB or SIB. Too bad. SIB is the SIB byte, so that would be confusing, etc. So here you go. You have these, which follow a nice pattern, these, which follow a different pattern, and these, which follow a third, but still different pattern. And there you go. So we have aliases for the low 32, 16, and 8 bits of all the registers. And for the original 4, we have an alias for the second to lowest byte as well, but only for those 4. Hey, Stacy, you may say, what about other registers? Do they have aliases? Well, you'll remember that we had aliases for the MMX registers, right? We had the floating point registers that were 80 bits, and we had the MMX that was 64. There were aliases. In addition, we have aliases that live in the vector world. The 512-bit AVR registers are ZMM0, 1 up through ZMM31. We have 32 512-bit registers. The first 256 bits of each can be referenced with a YMM0 through YMM31, and the low 128 bits of that can be referenced with XMM0 through XMM31. This is the evolution again, right? We had 128-bit XMM registers for the SSE extension. We had 256-bit registers for the AVX2 extension, and we ended up with 512-bit registers for the AVR 512 extension, right? Once again, not following any clear pattern in the naming, but following a nice clear pattern in the aliasing. So a question you might want to know is, how many registers are there? Have we talked about them all? We've covered them all, right? These are all the registers. They're not. And the answer is, who knows? It depends on the very specific chip as to what's there. There's a great blog post about it that you can read here from 2020. I like that. If you're super curious, go read it. There are a lot. There are a lot I haven't covered. And that's it.